time. So the Matlab is a programming and a numerical computing environment that's been used for millions of engineers and scientists around the world to do develop algorithms and models. And it has been used for developing many applications in various industries of different disciplines. So that includes physics, neuroscience, biological science, and all the life sciences. Right? So this has been incredible. I have a presentation, so I will share that with you. I will ask the organizers to send it out. So I'm not going to do it very today. I'm not going to talk about too much on that. And the tutorial session 1. So I'll briefly give what we have discussed. So that's basics using command line, and then we talk about arrays and matrices, and then how to write a script, especially the Matlab normal standard script and also the live scripts, and then how we can access help. So that is help is very useful because most of the there's a collection of thousands of functions and then maybe hundreds of toolboxes. So there can be a lot more that you cannot remember. So therefore, always you can access the help. Can read what all these commands is saying, and they give examples as well, so that will be easy for you to follow. And we talk about built-in functions, and then how to plot graphs, and then what are the special cases of functions, and how we can import and export data from different sources. So if you do experiments, so you need to get the data to the Matlab environment, and then you can create some output, then you can get that data, you can export that data for some other purposes. So let me briefly tell you what I am going to do today. So I will briefly introduce, give a review of basics that we discussed last time, and then start talking about a little bit advanced topics. So I will talk about Matlab as a programming language, especially it's a structured language. So we will I will introduce you the loops, and then the conditional statements and logical statements, how we can incorporate that into a script. Okay, and then the two special case, the important topics are the solving a system of equations and solving a system of differential or differential equations. Because these type of equations always come across, especially in biological sciences, not only biological sciences, but all the other sciences as well. But mostly you will come across as mathematical models for biological systems as a system of equations or differential equations, and especially toward the end of the session, so I will talk about curve fitting. That is also important because most of the time we will do experiments, especially biologists, they do experiments, and then they need some sort of fitting model for the experimental data. So I will give you some introduction to the curve fitting as well. So let me summarize some, let me review the basics that we discussed last time. So we start with the command line. So in the Matlab you have the editor tool, editing environment, and then the workspace, and then also the current folder, the manager, file browser, and then the command window. Towards the bottom, you have the command window. So you can input most of the commands, and then you can get output. So there we discuss how we can save this history of the command lines, and then how we can clear all these variables that we put into the command line, and especially we can use the command line as a scientific calculator. So that we discussed last time, and I have a live script for that, so I will share you this with you as well, so you can have it leisurely. Okay, then we talk about arrays and matrices. So the arrays and matrices in Matlab, there's no difference between arrays or the vectors and matrices. So you can simply create a vector or matrix using square brackets. And also we talk about how we can create using sequences, and then how we can extract subset of values, subsets from matrices or arrays. So we can use linear index, or we can use subscripts, and then how we can augment a matrix, how we can introduce different values after creating, and then how we do the multiplication. There's two ways we can do that, element by element, and at the same time matrix multiplication. So I'm not going to talk about mathematics behind that. Of course, if you know the mathematics, then you can understand how the internal operations is doing. So, but especially in Matlab, you have special functions, you can do that. Okay, and then how we can concatenate different kinds of vectors or matrices, and then how we can reshape and transform. All these we talk about during the arrays and matrices. And these are, of course, the knowledge of these basics is essential if you want to go for advanced topics. Okay, and then we talk about script. The script is basically a collection of these Matlab commands. So you can save it, and then the good thing is then you can repeat that. The same task, if you do it command line, then you have to remember the sequence. But then what you can do is you can simply copy that commands into a simple Matlab script, and then you can run it very easily. If you can repeat it, you can get the repeating things done very quickly. And there are two types of scripts, as I mentioned, the live script and the standard script. Standard script is .m extension, has .m extension. And for live script, you have .mlx. The live scripts is the one that I'm using here, because you can put the code, and at the same time, you can put the text and images into the script. So it's good to share your work with the others, so that you can put all the introductory comments, how the things are done, and with the images, with images as well. Then the other can understand the code very easily. Okay, and then we talk about different built-in functions. Matlab already have most of the functions, the most important trigonometric and other mathematical operations as built-in functions. You can use all these functions for your computer, for your calculation. Okay, and then these functions can apply not only for just values for the numerical values, but also you can apply these things directly for data structures as well. You can concatenate these functions as nesting functions. So basically, you can use a function inside another function. That's also possible. So and sometimes these functions are coming with toolboxes. So that's why I did not talk about any specific toolbox, because if it is specific, of course you can. There are thousands of functions can be there in one toolbox. So that will be specific, but without going into toolboxes, I'll get the very basic introduction to the Matlab built-in function. So that if you have an understanding of this, you can use the toolboxes very easily. And then the special topic also, the graphs and plots. This is very important. Matlab can create very publication quality images. So the most of the researchers worldwide, they use Matlab for creating publication figures for publications using Matlab. And we talk about how we can add labels, and then how we can customize, for example, adding legends, and then how we can create 2D, 3D images, 3D plots, and how we can create subplots, and also for sometimes it's good to have animations if you want to explain some sequence behavior stepwise. Then it would be better to use animations as well. So we talk about a lot in graphs and plots. And then there are anonymous functions in Matlab as well. So you can write them in command line, and also you can write in scripts as well. So these functions without name, you can use these functions especially to create inline, so single line functions that can be used repeatedly again and again. So that will create also give you increase the efficiency of the code. So we talk about those as well. And then the special case is the function. So that is also very important. So the function is also you have the live functions and normal standard functions. The live functions, again, you can incorporate images and more text as this descriptive text into the function. Other than that, there's no much difference between the function and the live function. So the function prototype is something like this. You can have inputs and you can have outputs, and inside the function in the syntax, you can include whatever the computation inside the function. So So you can use the built-in function inside the functions as well. So writing a function will be helpful. So then you can simply give your inputs and then you can get the output without writing down the same thing again and again. So you can store this in your Matlab path and you can reuse that for some other scripts, other computations as well. And then last but not least, the important topic is the import and export data. Because most of the biologists, they do experiments, a lot of experiments, so they have a lot of data. So you can get all these data so they into the Matlab. So they can be CSV file and there can be the data stored in Excel sheets. So you can import all these data and also you can do the other way around as well. You can export data into the Excel files and then into the CSV file. So you can use these data in some other purposes. So we talk about different ways to import and also different ways to export. And also you can create, generate a code after importing or exporting so that you can simply running the code, you can do the importing and extracting to the Matlab space very easily. Okay, so all these has been included in different live functions, so the live scripts. So I have created these for you. So I will ask the organizers to send these to you all as well. So you can actually do learn the techniques. Okay. Okay. So that's all for the review. So let's start today's session. So I will, as the first topic, I will talk about Matlab as a programming language. So this is the script file that I created, and basically here I'm going to talk about what are the logical statements that we can use in a script, and then what are the logical operators, and then what are the conditional statements we can use. That is basically then conditions, conditional statements, and then loops, for loops and while loops, because these will be useful when you do very complicated, if you want to write complicated computations as a single script file, then you will use these techniques, these structures. So therefore, all these structures are built into the Matlab, so you can very easily use. There's a syntax to follow. So if you follow that, so you can get do the what is the necessary task. So the logical statements. So let's begin with the logical statements. So these can be, there are two types. You can use the relational operators and you can use logic operations as well. The relational operations are something like this. If you want to compare, of course, if you want to create some conditions, then you will have always create something, some value with the other. So there are different operators available. So you can have exactly equals, greater than, less than or equals. These are the operators that is in Matlab. And as most of the cases, if it is true, if this is true, so it will be 1. A numerical value will be 1. If it is false, you will get numerical value 0. So this is also belongs to class logical that is defined in the Matlab. Okay. So some of the examples are here. So for example, if A equals 2 and B equals 3. So we will start with the basic, the very simple one, because if you know the simple one, so the most of the time, if you want to learn, so you have to do it with the simple, you have to start with a simple problem, because then you know the result, then you can compare. So if you start with a complex example, then you don't know the result, then you don't know whether it is true or not. Okay, so it's always better to, if you learn something, of course you all know, so it's better to start with a simple one. So that's why I put these simple stuff. So in live scripts, what you can do is you can create sections. So then if you click this blue bar, so you will run only these sections and you will get the results in the other side. I hope you all can see this. Is it? Can I get the feedback? Can you see the?
We can see, sir.
Running up. Okay, thank you. So here, so for example, if you do not put the semicolon at the end, so you can see the result here. If you did put the semicolon, then the result will not be shown as in usual syntax for in Matlab. So whether this is true, so the A is equal to B equal 3, and so the double equal is just to check with B 0, and then you can assign these even the statement whether it is true or not. You can assign that into a different variable. So this type of techniques will be useful when you put this into a for or while loop. Okay, so you can see that. So this is not, then the test one will be value will be 0. So you can use this test one for the conditional jump to another. For example, if you can check this test one to do some other thing. If it is 1, you can do something. If it is 0, you can do some other thing. So, and also you can simply add these variables to get the results. So this is also sometimes will be useful. Okay. So for example, if you check all these conditions and whether you want to know whether there was a one true. So for that purpose, you can simply add them all together, and then you can see whether there's how many truths were there. So for example, here there are total true. Okay. So it's simple, but of course you can make it complicated. And so for example, so you can apply these conditional statement not only for simple values, but also you can put that into structure. For example, you can create a data structure, so the array or matrix, something like this, and then you can test whether every value in array, so any value in array is less than or equal to 2. So how many values are there such which satisfy this condition, something like that. So you can apply this relational operators not only for just a single number, but for data structures such as arrays and vectors and matrices as well. For example, so here, so this is the random integer values of less than 10, and then it has 3 by 4 dimension. So this is the my data matrix. So all the numbers are between 1 and 10, and you have 3 by 4 matrix. And then if you test my data less than or equal to 2, so you can see that. So the less than equal to is only these 3 variables. So you can see test my data will give you once for one logical value only for this condition is true. For it will check every element of the matrix, and then it will give the result as the collection. Okay. Then if you want to find out how many true, then you can sum all these using sum command. So for example, how many matches were there, so you can get the result very easy, quickly. Okay. And alternatively, without using this, you can also use this find command and the number of elements. So how many are true? Find my data less than or equal to, so that will give you the same result here. And then the number of, this is num el is the number of elements, the positive elements. So you can combine these two to get the same result. Okay. So the which are true. So in the find command, you will get only the indices for the correct results. Okay. Whether this condition is true, so you will get only the indices. So the indices we discussed last time. So the indices for a matrix will start from the left top, and it will go down, and then start from the next one likewise. So it will be 1, 2, 3. So that is 3. Then 4, 5, 6, 7, 8, 9, 10, 11. So it is. So all these are the indexes for the matrix, for the corresponding matrix. And then how many true? So you can simply get the number of positive elements, something like that. Okay. So these are straightforward. So I'm not going to spend too much of time, but you can, when you have these files, you can go through very quickly. And then the other logical operators are these logical functions. So you can use AND or XOR or exclusive or not gates. So these are logical gates. So this kind of information can also be used to compare different values of different conditions, logical operation, logical conditions. Okay, and so similarly, you can assign that into another variable to get the what is the value. So if I run this, so the clear vars will clear all the variables previously we created, and then A and B, we have A and B, and then A equals B. So it will test, and these are the same, but at the same time, you can use the logical operators. The operators A and B. So you can, so these are logical values, and then you can compare these logical values using and, or, and exclusive, or, and not. All these are possible. Okay, so these are the notation for the and. This is for and this is for or, and this is for not, and this is for the exclusive or. You have a function. Okay, so you can compare and you can check whether these are true or not. So depending on this A and B from the previous run, you have values and you compare A and B, and then the results are here. Okay, so that's straightforward. So I'm not going to talk too much on it. And then you can use the logical operators to compare values in two or more arrays. Okay, not only as I mentioned, so it can be applied. These logical operators can also be applied to compare different number of different arrays as well. For example, if you have collected data on the number of beetles found in each, so you do an experiment. So you pick 6 locations and at two different time points. Okay, so in timeline you have the number of 6 locations. So these maybe you have a grid. You did a grid search and then you found this much of beetles were there at time 1. And then maybe after 1 or 2 hours later, then the time at that time you have the same grid structure, but you have different number of beetles. Then if you want to identify the locations in which at least 5 beetles were found at time points, so what can you do? So you can simply at least at different time points, so at least 5, then time 1. So this is the structure. If it is greater than or equal to 5, so you can convert this into a logical array with the logical values. So this is but time 1 is numerical. The elements are in numerics. But if you do this conditional operation, so not the condition but the logical operation, then you can convert that information to a logical value. And at the same time, you can do that for the other one as well. Then if you want to test whether the time 1 is logical or not, of course I have to run this, and these values were not. So if I run this, so you will have the result, and then I can run this again. So you will have, so always you need to create this time 1, because I click here without running this one. So therefore in the workspace we did not have this. So therefore, because we had run this beforehand. So now you have the results. So you can check that these two arrays, these two values are logical. Okay. And then you can combine this, because if you want to find location in which at least 5 beetles in both time points, so then we can. So we have individually, we know the time 1 GE5 and time 2 GE5 gives you where the locations where at different time points where there are at least 5 beetles. So if you want to combine at both times, you can use the AND operation to get it. Okay, and then so likewise you can do a lot of operations here. So here we have done. So you can see. So there are the grid, and you can find at least 5 beetles in this one, and at least 5 beetles in this one. So we have these two locations, two time points. Okay. Okay, so that's very basic for logical operations. And then these logical operations can be put into a conditional statement because you need to test a condition. The condition can be obtained from those logical operations. Either you can use the logical statements or operators. Okay, and then you can use the if else conditional statement, because then you can test whether one condition is true, or then you can do some task, and if it is false, then you can do another task. Okay, so this is the very basic example. I hope most of you may have seen this, so therefore I will quickly go through again. So there's a random value to generate, and if it is less than 5, of course it will then go into the, because if it is less than 5, it will go into the loop, into the condition, and then it will print this. Of course 0.49 is less than, so then, and then after that, after executing, it will jump to the next line. So this is the last time. It will always go to this line, because this is not inside the loop, and then the random value is 0.49. So if I run this again, so now you can see, okay, it's 0.14, it is again less than 5. So if I run it again, okay, now 0.9, 0.92. 0.92 is not less than 5, so it is not going into the inside, into the conditional statements. Therefore, it will not print is less than half, but it will print the last line. The random value was 0.92, something like that. Okay. And if you, so this is a very basic, without using the else statement. So you can combine else to do another task, like if it is wrong. So this is what we do. So if you can combine, you check, and then if it is less than 0.5, so you do some operation. If it is greater than 0.5, the strand will generate the numbers from 0 to 1. Okay, then there can be numbers greater than 0.5. So then you do something else here. Okay, so you can run it, and then you will get the result. So here also you can understand it easily. So I'm not going to too much. I hope that is fine with you. Huh? Because these are very simple. And of course, you can add more options. So you can use without using else. Then you can check again by putting else if. So if some condition, and else if this condition is satisfied, or it will do this one. If it is not satisfied, you can do another condition. For example, if you want to separate the marks of the student to different classes, whether it is fail, pass, or has distinction, so you can use something like this. It is test one, and the next one, and the next one. And once condition is met, one condition is true, the remaining conditions are not tested. So that's the case in the Matlab else if function. Okay, and the alternative actions will not be performed, even if some cases, if you write some in some way, it will not test the others. It will come out from the this conditional statement. Okay, if it is true, it will do this one, and it will go outside the if and if. Okay, and also we can combine these as nested loops. That means you do, and you within the if statement you can have another if statement. You can test another condition. Okay, so the nesting is possible. You have a test for one condition and do another test to do another condition. For example, the course of action depending on whether the patient has a rash and their temperature. The temperature is high, then you do something else. And if both are true, if he has a rash and the temperature high, then you do something. If it has rash and temperature is low, you do something else, something like that. So for example, so we have rash options, yes or no. The rash, so this is just to get a value from these two. So this is a binomial distribution. So we have some probabilities given here. So accordingly, if I run this, so the rash option, sometimes it will be yes, sometimes it will be no. So this is just to simulate whether the condition. Okay, and then the red temperature, again we generate the temperature value, integer value between 36 and 42. If it is greater than 40, so the check is this. So then we can simply write down the format text. This is just to combine these two together, and then you can put that information into the output, something like this, by using this command, format text. So you combine this together with this result. Okay, so that's just to combine this. So you have the format text. So this will be output as a display output as the output, and then these two %d and %s value will be this temperature and rash option. So here is the logical statement. So if you compare rash, so the rash there will be value at rash, it is a string, and you come this string strcmp is just to compare this rash and this string. So if these two are matching, so it will go to this loop, this not loop, this condition. It will go to statements, these statements. If it is not true, if it is no, then it will do this one. But if it is going inside, then again we test for the temperature. The temperature is greater than 40, so you have one option, treat immediately. If it is less than 40, so you can check again after 4 hours. Okay, so whether the temperature is going high or not. If he or she does not has rash, then it will go to this section, and again no rash, and then you can test the temperature. This temperature greater than 40, then you can check again in 12 hours, not like in 4 hours in the previous case, because no rash, and no rash, and at the same time temperature is less than 40, so you can simply discharge, like something like that. Okay, so this is just to show you what we can do with, by combining different by nesting if statements. Okay, so if I run this, so you can see that, so the temperature was 40 here, that is this temperature 40 degrees, and the rash, yes, 40 degrees and rash, yes. So what should be the case? Rash, yes, this one, and it is not greater than 40, it is just equal to 40, then it should be this one. Check again in 4 hours. Check again in 4 hours. Okay. Okay. So then the other important one, the conditional statements, not the structure is the loop. Okay. So the loops can be, there are two types of loops. You can use for loops and while loops. So the for loop is basically to repeat a task for a predefined time. So if you know the number of times that you need to run again and again, then you can use for loops. But if you do not know, then you can use while loop. You can have a condition. Condition is met. You can break out from the while loop, and you can come out from the loop. But of course, that's some tricky one. So if you miss, sometimes it is possible to get an infinite. So if you miss that condition, if you do not write properly without considering all the cases, sometimes you will get an infinite loop. So that will run again and again. So when you use while loop, you have to be careful. But for for loop, you have a predefined number of sequences. So you can use this. So this is the syntax for. So you have the sequence, and then you can within that sequence you can use what you should do for one particular sequence. So then it will repeat for example here it will repeat for 5 times. So if I run this, so you need to see I love Matlab, I love 5 times because it goes from 1 to 5. Okay, so the sequence can be of any array as well. For example, so it can be, it is just count the number of pairs. So you can use these sequence values inside, but if you do not use, you simply use the number values. For example, if I run this, it will be the same. Okay, so you have 5 times values, and you simply display something without using this information. Of course, you can use this information. I think I have an example of that as well. And even this can be a cell array. So cell array, so you can use anything just to get the any number, so that will do the sequence if you are not using this. But sometimes you use this inside to make it more complex. Okay. Then the current value of the sequence can also be used, as I mentioned. So this is a sequence number. You can use it. So, for example, if you want to use this in cell array as well. So, if you want to use this information, in the first run, it will use this, the first value of the array, and in the second run, it will use the second part. So, if I run this, the first case you will simply have I equals 1, 2, 3, 4, 5. So we are using the I value on the I value. In the second one, in the first run it will use a lot, and in the second run it will use it is great. So I love Matlab a lot. It will be the first because it's the first one, and then loop number, and this j you can use to something else for some other purpose. Okay. So if I run this one, you can see. So it will display the loop number is something else. So the loop number will be going from how many, depending on the the value. So this is 14. Start with 14 and subtract 3 at each time, and then it will go until it's 0. So you can see start with 14 and then 11 and then 8, then 5 and then 2. Okay, and at the same time, so you can plot what is the sequence. Okay. And then for increasing in the sequence, the current value of the sequence can also be used as index. So that's also good. So sometimes if you have an array, then if you want to change the value of that array, so you can put that as a sequence because it is increasing. Then you can create an array with, and also you can access all these array points by putting that into the as the index to the array. Okay, something like that. If I run this, yeah. So the g cube is basically you get the value first one, and then you get the cube. It should be 1, and if it is second time, it should be 8. Okay, and then it is 1, 8, 27. It is increasing, but n. So this is an array. So it is just n1 will be in the first run. It will be n1. So the first element will be 1. In the second run, the first element will be 1. But in the second run, it is 2. So this is n2. So you have two more elements, 1, 2, and then it is increasing. 1, 2, 3, 4, 5. So your array is increasing in size, and then you put that the array value as the index. Okay. So you can do a lot. So this will be useful when depending on your requirement. And then creating a new array with using an arbitrary sequence of values, that's also possible. For example, if you want to, so this is the arbitrary array, arbitrary data. And then if you want to put this into another array and use this information to put that into that array, so that is also possible. So this is SQR data. So this is what is needed. And of course, you can do this. So this is just to pre-allocate. Sometimes it is better to pre-allocate. If you know the structure of the array, it's better to pre-allocate the memory. So you can create, this is a built-in function, 0s 5 by 2. So that will create 5 into 2 zeros matrix for an array. So you can see that array. So then, so this is the indexing. So you have to start with 0 and then n equals n plus 1. So that's the first index. So in the first run, it will be 1. Then SQR data. So this is 1 into 1. So what is 1 into 1? So this is 2. So see 5 by 2 matrix. 5 by 2 matrix. This is the first column and this is the second column. First column will be your data. So your data, you will have the first column. Okay. And the second column, what will be? It is the square. So if I run this, you can see something like that. So in each run, So in the first run, what happens? You have 56 and 3 as the first data, and then the second first column, and the second column it will be my data square. Okay, so it's 56 square. That is this value. But of course, you assign only to these two values, the first row. So if you do this, of course, you will have all the values will be there, but only you assign to the first value. So you take only this value. Okay. In the second run, so it will be 2, 2, 1, and 2, 2. So the 2, 1. So the first one will be there, is not intact, and then so you will have the second one, something like that. So you can do this. Okay. And at the same time, as I mentioned in the conditional statement, you can use the nesting for loops as well. So if you want to create the loop inside the for loop, that's also possible. For example, if you want to do times tables, so the times table is basically the kids do. That's the chuck rate. 1 times, 2 times, 3 times. So if you want to create that, you can simply start from equal 1 to 12, and then you have j equals 1 to 12. So you have a table with these indices. These indices value will be multiplication of value j. So the first one you will get the 1 times, then 2 times, 3 times, 4 times. So likewise. So this is a very simple example, but of course you can use this nesting to access to create depending on your requirement, you can use this information. Okay. For example, if you can systematically access all these elements of a table, of a matrix or array. Okay. Of course, so this is the for loops in computational point of view. It is a kind of expensive. So you can convert this into matrix format so that you can simply speed up the process. So the same thing can be done by this one as well. Okay. If I run this, and so this is also helpful when you do the experimental protocols. Okay, this is a task that I have included just to simulate the serial dilution. So I will not go through because we have we have time. Of course, we can go through this one leisurely when you have this file. Okay, so this example, okay, again, so this is also if you want to find out, so you have a DNA sequence, and if you want to find out whether there's another part of it, whether this part is present in the previous DNA sequence, so this can also be used within a for loop. You can compare starting from the first element. You can compare the first 4 elements together and together again and again. Then you will see whether you can find which matches this sequence in this initial DNA sequence. So this can be done within this one. For example, if I run this one, so you can see that. So the result will be it will give you the location. So its alignment location is 10. So you can see it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So starting from 10, you have the same sequence. So this is just compare. Starting from the first one, you compare the sequence with the first 4 elements, and then you again jump to the next location, and you do the same again and again. Okay. And then the while loop, that's also important. So as I mentioned, so you have to be careful to make the condition. So you have to put a condition to come out. Okay. And so this is an example. So while, so it start with n equals 20, and then while n is greater than 5, you will do. So in the first run, n is greater than 5, 20 is greater than 5, so you will go inside it, and then you will generate random number. Of course, the maximum is 20, so at some point this will generate a value which is less than 5. So there is a possibility to come out from this. Okay, so if I run this, then it's 1. Okay, so it's come out. It is not. So of course, at the end, it will come out. So again, if I run this, n equals 2, So now, okay, so now we had initially 9, 8, 16, 16. So it's all greater than 5. So it ran again and again, but final value is 4. So therefore, you came out. Okay. So this is also can be used to simulate the Fibonacci sequence. So I'm not going to do this example as well. So this is you can follow the same thing. Only thing I have put the while loop in a while loop. Okay. So this is what I mentioned. So it's important to have a body statement where the value in the conditional statement gets updated. Okay. So otherwise you will get to an infinite loop. So when that happens, it will show you busy in the bottom. So then if you want to come out, you can simply press Control and C to break it and come out. Okay. The other type of structures that can be used is a switch case or otherwise. So this is you check the case. So the statement you have different cases, and you check that case whether that case is valid with a condition, and then if it is true, you will execute that the whatever the content inside that case statement, expression. Then you will break up something like that. For example, if you want to, so this can be done for single values, or this can be done for multiple values. For example, in the single values, so generally you are asked to enter a number, but you can give a number here. So if it is n is 2, so you have different cases. You check the n and switch n. So you check the n variable. If it is 2, if it is -1, then you display this one. If it is 0, you display 0. If it is 1, you display positive 1. Otherwise, you display other value. Okay, in this case, it should be other value. Because n is 2, so it will satisfy only this condition. So that will. So this is also important for certain examples. Okay, certain depending on your requirement. So this can be used instead of while or for loops. There are no loops, but you only check the condition and then you whatever the necessary it will attain. So this can be you can compare multiple values elsewhere. Okay. So for example, so you have x values and then you have plot type and switch plot type. So the plot type you can do different numbers. So depend on in this case, it only expects bar, pi, 3, and something else. Okay. So you can check whether this plot type or else you can it's running. Okay, something like that. Okay. Okay, so that's a very brief introduction to the Matlab, different structures that can be used to create complicated scripts. Okay, if you want to do a complicated task, then you can combine for loops, else loops, switch case loops, the statements, and then while loops, so that depending on the repetitive task, depending on the requirement, you can combine and write up. Okay, so I will stop for this section, and then the one of the important topics. I think so. We will do the question and answering at the end. Is that okay, or do you want to do it now? So it's up to you. What do you think? If you have any questions, so it should be asked now or later. So if not, we will do that towards the end. Okay. Okay. So the next one is this. So that is the solving system of equations. Okay. So that's very important. So this is in this diagram. I hope you can see. So I simply put as the mathematical modeling process. So the modeling process is you have the real world problem, and then you define the problem, and then you make assumptions, and then basically what you do is you formulate the real world problem, and then you make assumptions to, for example, if you want to make it linearized, or if you want to make it simplified, and depending on the assumptions, then you create the mathematical model. So what you need is your real world problem should be represented as a mathematical model. So that is the translate. And then the mathematical, if you have a mathematical model, then you can analyze, you can validate, and then you can get some output. Okay, so you make assumptions, and then you formulate the mathematical problem, and then you solve the mathematical problem. It can be analytically, or it can be numerically, and then you interpret the results, and then you compare with your real world problem. It is a match, so you will use this model as the computational model for the real world problem. If it is not, then you have to redo, redefine, or fine tune, and then this is a kind of loop. Okay, to do this, most of the case analysis S backslash b is equivalent to a dot slash b. So it's simply the 1 over b. If A is a square matrix n by n, then B is, and also the B is a matrix with n rows, because this is n by n and this is n rows. So both are same, rows, number of rows are the same. Then x equal a backslash b is the solution to the equation of this. If it exists, so that will be the solution. Okay. And if A is a rectangular matrix m by n, and m is not equal to n, and B is the matrix with m rows, the number of rows are again equal in A and B, then A and B returns the least square solution system of equations. So I will talk about this when we talk about the curve fitting. So you can use this technique to fit a curve, linear curve to experimental data. Okay, so the most of the cases, if you want to solve, so you need to have these conditions. Okay, of course that is true if you have a number of unknowns. You need to have, if you want to get a unique solution, you need to have a number of equations. Okay, so if the solution exists, you can use this one. Very simply. Okay, let me use a very example to show this. Okay, so consider the following example. A dietitian plans to provide a patient with a meal that has 70 grams of protein, 100 grams of carbohydrate, and 820 milligrams of calcium. So this is the required amount. And each serving of fish, vegetable, and energy will have different portions of proteins, carbohydrates, and calcium. The fish, one portion of fish will have 28 proteins, grams of protein, and 36 grams of carbohydrate, and 200 milligrams of calcium. Okay, something like that. But the dietitian wants the patient to have 70 grams of protein, 100 grams of carbohydrate, and 820 milligrams of calcium. So if you put this into a system of equations, so the first one, what it says, so the 28, if you assume the A, B, C is the number of servings, fish, vegetables, and drink. So the number of servings we know, then 28 per serving, you will have the protein. So 28A plus 6B plus 11C should be equal to 7. So that's the first condition for the protein. And for the carbohydrate, the number of servings for fish is 36, then 36 into A, and number of servings for vegetable is B, then 36 plus 36B plus 10C should be equal to 100. So you have this system of equations. So this is simple, but of course, so you can it can be complicated ones as well. So this is just an example to try. So this is then if you know this one, you can simply create the coefficient matrix A 28, 6, 11, 36, 36, 10, 220. So we have discussed the semicolon. After putting a semicolon, it will go to the next row. After putting semicolon, it will go to the third row. Okay. So this is the matrix, A matrix, and this is the B matrix. So it should be a column matrix. So that's why this transpose, this dash simply. So I have created a row matrix. By putting dash, it will go to it will become a column matrix. So now we have the condition. So the system is AX into B. So that's this type. Therefore, the solution ABC will be equal to A/B. I hope that is clear. So first I will create the system of matrices A and B. So this is A and B. Okay. A matrix and the B matrix and the solution. So I can create this, I can get the solution two ways. A/B or ML divide A. So and also there's another method. So if we can create if we can combine the augmented matrix, combine the A matrix with concatenate A with B in the row as a column, and then if you do the if you apply the algorithm row reduce the Gauss-Jordan elimination to get the row reduced echelon form, then you will simply get the final result at the last column. So that can be done very easily using RREF, this function in Matlab. So the row reduced echelon form. So basically use. I will very briefly give you first. First check the first results. First one here, A/B. So you have the results 2.5 and 1. So what you need is 2% of fish, 0.5% of 0.5 of vegetable. Is it vegetable? No. What was it? Vegetables, and then 1% of drink. Okay. So the same result you can obtain using the ML divide. So this is the result. So if you follow this, you can satisfy the given conditions. And so this is the row reduced echelon form. So that basically you start with A and you do the operations, and then what you do is you convert the A matrix into identity matrix. When you do these operations, then you will do the same operation into the augmented part B. So the B start with 70. So the B initial value will be 70, 100, and 820. But when you do these operations again and again to obtain the identity matrix in the first half, as the A converted into I, then your B will be converted to your result. So this 2.51 will be this. Okay. So this is very easy. If you have it, the only thing is you need to formulate the problem. You need to find the coefficient matrix and the B. So that will be easy. The solution, you can simply use this one of these techniques to obtain the solution. Okay. So our system had a unique solution. So that's why is that? So the number of variables I equal the number of different equations. What happens when the number of equations are different from the number of variables? So in that situation, so operator will give you a warning message. For example, in this case, so let me check. So you have A as this matrix and B as this matrix. Okay. By looking at this, so you have A matrix and you have B matrix, and then when you use the backslash operator to get the solution, X equal A backslash B. So there's a warning. Matrix is close to singular or battery scale. Okay, results may be inaccurate. So that is case. There's something going on. So what will be the solution? So solution is something like this. But of course, if you get this RREF form, raw reduced echelon form, so then you can see that your answer will be something like this. So you have 1, 1, and you have zeros in the last one. Okay, so this is something to do with the rank of the matrix. So we discussed this when we talk about the basics in the last session. So the rank is less. That means the number of linearly independent equations are less than the. That's basically effectively you have only 2 equations in this system, not 3 equations. Okay, so therefore you can have infinitely many solutions in this case. So if you have this raw reduced echelon form, you can convert this back into the matrix form. Okay, so if you can remember, we had this linear system of equations, and we wrote down this A matrix by looking at that. But we can do the other way around as well. So if you have this, so the first variable will be A, and the second variable is corresponding to B, and the third variable corresponds to C. The first equation should be A minus 2C should be equal to 1. And the second equation should be 1 times B plus 3 times C should be equal to minus 2. And the last one should be 0 times A, 0 times B, 0 times C should be equal to 0. So that's true. The last equation is always true. So 0A, 0B, 0C. But these two will also be true. So only these two are the effective equations for the system. So these two, the variables that has one coefficient in front of in the raw reduced echelon form is known as the leading variables, and the other variables are known as the free variables. So the we can write these leading variables in terms of free variables. Okay. So for example, in this case, if our free variable will be C. So if we set the parameter to C, so for example, if C is T, so this is just a parameter. So C can have any value. And in terms of C, we can write down A and B. In this case, the A should be equal to 1 plus 2C. So the C is equal to T. So our solution will be A equals 1 plus 2T, and B equals minus 2 minus 3T, and the C equals T. So by taking any value for T, so you can have infinitely many solutions for this problem. Okay. For example, even though it is badly conditions in the A/B, it gave a solution, and that solution is one of the solutions. For example, if you put T equals minus 1.2345, so 1.2381, then if you substitute for the B and A, you will end up these two values. So it is one of the solutions. Okay. But it was not intuitive, but it gave a warning sign. Then it's good to see the RREF format, raw reduced echelon form. By looking at that, you can guess whether it has infinite solution. Okay, then you can get a parameterized solution for this problem. Okay, and on the other hand, if you insert matrix. That is actually one of the solutions for this. Okay, so if you have x1, x2, all are 0, 0, there's no carbon or oxygen in the left hand side, there's no carbon, the resultant will also be 0. So that is known as a trivial solution of the homogeneous equation. So this backslash operator will give you a solution that's 0. So that's true, but it is trivial solution. But we are not interested in that. Therefore, we will go to use the RREF format. So the raw reduced echelon form. So you put the A and we concatenate B, and then you use this command to convert to the raw reduced echelon form. So that have this solution. Okay. there you will get something like that. So this is, of course, so we should not have this. We need to convert this into rational format. Rational format is so to convert that into rational format, you can change the you can give a command to Matlab as format. Right. So this will continue display the resultant in rational format. So if I click here, so of course this is 3 by 5. This is also 3 by 5. So it is not showing here, but if I click here, so you can see everything, because the screen is small, so that's why it's hiding. But so your result, so if I put that you can equate that the row reduced echelon form equals the same thing. So you have this solution. So you have A is the identity matrix, and the last part, is not the last part. Fourth column is -103, -706, -203, and the last column is 006. So if I convert this back into our system of equations, so you can see that this is the leading variable. X1 should be equal to, if I put the fourth one, the fourth variable X4 as the parameter t, so that should be equal to 1/3 of t. Is that clear? I hope that is clear. Yeah? Because minus sign is the sum x1 minus 1/3 times t will be equal to 0. But if I take that minus sign to the other side, so that's this equal. And then the x2 will be equal to 7/6 times t. x3 will be equal to 2/3 times t, and the x4 will be our parameter variable t. So you can have many number of solutions, but to obtain the simplest one, you simply put the t equals 6, and then you will get the corresponding results. So that will be 2 times x1 will be 2, and the x7 will be x2 will be 7, and x3 will be 4, and x4 will be 6. So that will balance the equation. Okay. So the solution is something like that. So this is the solution. Of course, since the minus sign is there, so I simply multiply by 6 by getting the fourth column of the solution, and multiply by -1 to obtain the positive values, and then multiply by 6, and the last parameter t will be 6. So this is the solution of the examples that we can use for. And of course, so this is as I mentioned, there are different methods, different techniques. Another method is the lin-solve command. So that's a solving linear system of equation. So for this purpose, you can use the symbolic math toolbox if you want. But of course, so that toolbox should be installed. But this is just to show you. But of course, for the lin-solve, you do not need the symbolic math toolbox. This is if you have symbolic math toolbox, you can even simply you can write down the equations as given in the coming as the system of equations symbolically, and then you can simply create the A and B matrices by using this simply. But of course, since you know to create the A and B matrices by looking at the system of equations, sometimes maybe it is not easy, but of course, yeah, I mean, this is just to show you that you can use the symbolic toolbox to convert these system of equations to A and B matrices. If you know A and B matrices, and as in the previous cases, we can simply use the lin-solve command, lin-solve A and B. So this will give you the solution. Okay. So if you use the symbolic toolbox, this is to define the variables A and B as symbols A, B, C, and this is the format to show you define the equation. So the equation 1 equals 28 times A plus 6 times B, 11 times C. So you need to put double equal signs to make it equal in the symbolic maths. Okay, 70. So this is the equation 1, this is the equation 2, this is the equation 3, and you can use the equations to matrix function in Matlab to convert these equations to A and B matrices, coefficient matrix and B. And here the equations, and this is the variables. So these are the inputs to the equations matrix. So equations you can define this way, and the variables are A, B, C. Then you can come directly get the capital A and B. So then you can use this linsolve command very easily. So that's in the previous case. So it's like ML divide. So it's just to so if I write, so this is A matrix given from the equation to matrix, and this is the B matrix, and your result. If you write linsolve A and B, you get the result here directly. Okay. And at the same time, you can use the solve command as well. So you can, so as I mentioned, the linsolve can be used without even the without using symbolic maths. But solve is can be used without creating A and B. You can directly solve the equations by using solve command. For the linsolve command, you need to A and B. So A and B can be obtained from either from the symbolic maths, or you can directly write down A and B. I think we can write down A and B directly, and you can use the linsolve. And if we sometimes if we do not want to find the A and B, and then we can use the solve command. Of course, then you need to use the equation 1, equation 2, and equation 3 in the symbolic maths. And of course, in this situation, you can even get the results as symbolic examples as well. Okay, so in this, if I run this, so this is the same. So you will get the solution, the single solution, the solution. And if you want to A, B, C, then the solution will have to access the variable. You can use this dot notation. Solution dot A will give you the A. Solution dot B, solution dot the same result. But if you can use this solve command to even to nonlinear complicated problems as well. So you can get the equation in expression format, analytical as an analytical solution as well. So if you have symbolic rule, since x, y, a, b, so these are the two equations. One is the equation of circle, x squared plus y squared. So that you can see that it's nonlinear. And of course, then in this situation, you cannot create even A and B matrices. And equation 2 is x minus 1 equals b. So if you want to solve these two equations, you can use the solve command. Solve, you have the equation 1, equation 2. Our variables are x, y, and the result will be x, y. Okay. So of course, since this is a quadratic equation, so you can have for each of these x and y, you will have two solutions. So altogether, you will have two pairs. Okay. So we can see that you can get the solution as a symbolic format as well. So your x, two solutions for x will be this b minus b02 minus this and that. So this is positive and negative. And then if you want to access these two, so the pair will be corresponding to corresponding rows. The rows will be matching. So if the x solution is the first one, then the y solution will be the first one of its vector. Okay. And if you are going with the second solution of the x, then you need to go to the second row of the y solution. Okay. So that you have to keep in mind. And of course, you can use these x and y to create a subsequent calculation as well. So if you define a symbolic variable z, and if you want to do a dot product of this, the first solution of the previous equations, so you have the x1 and you have the y1, and if you want to get the dot product of these two, and you can use the dot xy, and you can simplify the equations even as well, even further using this simplify command. Okay, so you can do a lot more. So for example, your x1, as I mentioned, you can get the first result of the first, and then the corresponding y results will be y1, because these are two results. And if you want to compute the dot product of x and y, so this is the result dot product. The dot product is basically you multiply the x1 with y1 plus x2 with y2. Okay, so this is the dot product, and if you, then you can use the simplify this solution. So the final result will be this simplified version. Okay, so that's all for the linsolve and solve commands. As I mentioned, so now we have talked about three methods using backslash operator, and then the linsolve, and then solve. And then I also mentioned that we can use the inverse of the coefficient matrix. If it is exists, then we can use the inverse of the A matrix to simply compute the solution. So our system of equation is AX into B. So the X should be A inverse B. Okay, for non-singular coefficient matrix, non-singular is basically your A inverse is X. Okay, so the determinant of A is not equal to 0, then you can use the solution as A inverse B. A inverse can be obtained if you know the A using INE command in Matlab. So that's very easy. Okay, so if I click here, so this will be, so of course, why is this all this in fractional format is the rational format, because I have put the format into rat in previous location. Okay, so if you want to go back, you are simply revert it back. But anyway, so this is the solution, that's all I'm saying. Okay, so this is the inverse of A, and this the solution is basically given by inverse of A multiplied by B. So this is the same solution, 2.511 for our previous example. Okay, and yeah, this is that's why. So if you want to find out the inverse of the matrix, you can use this row reduced echelon form as well. So in the previous case, what we did was to solve the system of equation by concatenating A and the B. But if you concatenate A and the identity matrix as the next as the augmented matrix at the combination, then A will be reduced to identity matrix, and correspondingly after these operations, I will be goes to convert to its inverse. So that's the idea. Okay, so you can use RREF format. So you start with A and identity matrix. So the identity matrix is you can create by I3 by 3 identity matrix. So the 3 by 3 identity matrix is this. Okay, so initially you had A in front of towards the left side, and then the right side was the identity matrix. But if you do this row reduced echelon form, if you follow the Gauss-Jordan method, then it will convert, the A will be converting to the identity matrix. At the same time, your identity matrix will be converted to the inverse. So that's true. So that is the same that we got from the inverse equation previous. So this is that. Okay. So you can use this inverse to obtain the solution. So of course, you need to check for the singularity. So the computing the determinant of the matrix, that you have a Matlab function determinant of A. If determinant of A is not equal to 0, then it is singular. Okay. Then you have multiple solutions or no solution. Okay. So this only the condition is you need to compute the determinant. If it is not equal to 0, then you can find inverse. Then you can use the inverse of the A multiplied by B to obtain the solution. Okay, so what happened for singular coefficient matrices? If A is singular, the solution AXB either does not exist or is not unique. So the backslash operator, as in the previous case, issues a warning. And if A is a singular and AX equal to B has a solution, then that solution can be so A so it will give you a solution, something like that. And if we can check whether this is a solution, we multiply the A into the solution, that should give you our B, because our X equal to B. x, that is the A solution, should be give 5, 2, and 12. Yes, 5, 2, and 12. So it is given here. So this is our solution there. So the pseudo inverse gave a solution whether we cannot find the solution from previous two methods. Okay. So that's all for the system of equations. I think it's clear. So I'm a little bit fast because we are got to cover. Okay, I think it's easy, so you can follow easily. But since I will give you this, all of these scripts, so I will ask the organizers to send all of you who registered. So you will have this. So you can run it and do it again. Of course, I have referred a couple of references. I have put these references in the as the top of the script. Okay. Okay, so that's all for the solving system of equations. So we studied four different techniques, and we applied for different intuitive examples in biology, and then we found ways to solve it. So let's talk about the other important one, differential. Let's have a break, maybe 10 minutes. Is that okay? Nadisha, is that okay to have a break?
Sorry, sir, I disconnected.
Somebody asking me to have a break. I hope that's fine with me as well. Maybe 10 minutes break. After just I will tell you. Okay, just a couple of minutes later. Okay. So the system of ODEs can be of this nature. Okay, any number of coupled ODE equations form a system of differential equations. In most of the cases, you will come across not just a single equation for the model, but many. Okay, so then you can create a system of equations for n number of ordinary differential equations with different dependent variables. So you can see that you can have y1, y2, yn up to n number of different variables, and you have each is given by a set of ordinary differential equations. So the differential equation is function of the rest of the variables. Okay, but the only one variable t will be the differential independent. Okay, then the function that encodes the equations should return the vector with n elements. That function should encode the differential, the solution, so the differential equation part. Okay. For example, if we consider the following differential equation with two variables, dx over dt equals y, or dy over dt equal xy minus 2. So this is a system of equations. You have two dependent variables x and y, and one independent variable, that is t. So if you want to encode this as a function, so you need to encode the derivative, that is y, and how to compute y and xy minus 2. So the function that encodes the equation look like this. So to write down this function is very, very important. So this is my ODEs, which is that the output should be the dx over dt or dy over dt is the time, and also the p vector. So that's p vector is basically your x and y. So it's assuming the p1 is x and p2 is y. So your first equation, your first dx over dt, that's dp1 should be equal to y. Y is p2, the second element of the p vector. And the dp2, that is the derivative of the y, should be equal to xy. So it's p1 multiplied by p2 minus 2. So this is to write down, a way to write down. Okay. So we will talk about when we discuss a couple of examples. And the most of the cases, not only the first order differential equations, you will come across higher order ordinary differential equations. So the Matlab ODE solvers can only solve first order equations. Therefore, what you can do is, so all the higher order ODEs can be converted. You can introduce a different variable. You can rewritten as an equivalent system of first order equation. Okay, what you can do is you can define all the variables, all the differentiation, the order of differentiation into just a variable. So, for example, y equals y1. This is the zeroth order differentiation, and the first order differentiation y2, second order differentiation y3, and the final one will be the n-1 order y. So by using these variables, you can convert the higher order differential equation as a system of first order differential equation, because you know that, for example, the y2 is the first order differentiation, and if you take the y3 and if you take the y2 dash, so the y2 dash should be the second order differentiation, because y2 equals the first order differentiation, and if you take the derivative of y2, then that should be the second order derivation, so the y order 2. So the y order 2 can be y2 differentiation should be equal to y. Likewise, welcome back. Are you guys there? Let's start. Yeah.
I'm
okay.
Here.
Okay. Okay. Yeah. Okay. Thank you. Okay. So let's continue. So what we talk about is if we are given, if we come up with higher order differential equations, what we can do is we can convert that into a system of first order differential equations. For example, ultimately your model will boils down. Let's assume that it's your model is of this nature. So it's a third order ordinary differential equations. What we can do is we can convert this into the 3 first order ordinary differential equations. So what we can do, we can substitute these 3, and then we can convert this into the first order system. Okay, so assume y1 is simply we replace y with y1 variable, and dy over dx with y2, and d squared y over dx squared as y3. So then we know that dy1 over dx, the y1 is one variable, and only the independent variable is x. dy1 over dx should be equal to y2. Why? Because this is the definition. dy over dx is y2, and we know that y1 is equal to y. So the dy1 over dx should be dy over dx. So therefore, it should be equal to y2. So the second variable. And then dy2 over dx. So this is the first variable and second variable, dy2 over dx. So the dy2 over dx means should be d squared y over dx squared. So that is equal to y3. And then if you take dy3 over dx, so the dy3 over dx, that is equal to d cube y over dx cube. So that can be replaced using this one. So we know d cube y over dx cube is equal to d squared y over dx squared into y minus 1. So we can take this thing to the other side. That should be minus 1 plus d squared y over dx squared plus multiplied into y. And d squared over y over dx squared is basically y3. So we can replace with y3, and y is equal to y1 minus 1. So now this first order differential, third order ordinary differential equation is being converted to 3 first order differential equations. So this is the system of equations. Here we have only first order differentiation. Okay, so that's very easy. So that's a way to convert. So it's a systematic way. So there is a systematic way. So you can convert that into a system of first order differential equations. Okay, so let's solve. So what is important is the numerical solutions to differential equations. So the most of the cases, some of the problems, these differential equations may not have analytical solutions. So always we can find a numerical solution. So the Matlab is very good tool, and there are a lot of solvers, ordinary differential equation solvers in Matlab. So they are given for different types. So there are different types. For example, these type of systems will come as stiff problems, non-stiff problems, and depending on on this. That's mathematical terms. I hope you all know the stiff problems will give you if you want to solve it. So then you will have to solve. There are a lot of variations in the parameters. So it can, for example, depending on that, your problem can be stiff. Okay. So to solve that, of course, you can solve it the same as non-stiff ordinary solvers, but then it will take time. So you will have to reduce the time step to solve it. So, but there are techniques, the optimized techniques. So accordingly, they have prepared different ordinary differential equation solver. So the most of the cases ODE 45. So this is a function that performs well with most ODE problems. If that is not, then of course you can use the other available differential equation solvers. These are efficient depending on the problem, whether it is a non-stiff or the so you need the accuracy or the depending on the accuracy, you can use one of these. Okay. So if I run this, so just to show you the ODE, help ODE 45, if you put this into the command window, you can get the information about the ODE 45. So this is the ODE solver, solve non-stiff differential equation. Okay. So if you go to the further down, so you can see, so there you have other types of ordinary differential equation solvers. So you can click and then you can see what they are for. So what methods and then what type of problems it is useful. But most of the cases we can use ODE 45. Okay. Okay, so let's start with that. So this is just to show you, if you want, if you're interested, please have a look in the other functions, other ODE solvers as well. Okay. And there are several example files available as an in the Matlab. So you can if you simply click run ODE example, if you put this into the command window and enter, so you can get all these examples. Okay. So all these examples will be there. So you can use this as a starting point. But I will simply not going to use it here. That's it. So let's do examples with our way. Okay. So let's talk about how to solve a simple linear ordinary differential equation. So it's better to start with the simple one. So this is the common model for population growth. dP over dt is equal to R times P. Okay. So it's the proportion. The rate of population is proportional to the current population. That's true. Okay. So how to solve this? To solve this, we need to encode the derivative to a function. So derivative dP over dt. That is the right hand side should be encoded into a function. So that function is the simple function. So this is the function that I have created. dP over dt equals simple PG. So you can put any number, any name. So the simple population growth. So the input should be the dependent variable and the vector, whatever the y variable, okay, t into p. So you can assume that r is a constant and it is 0.1, and the p. So the dp dt should be the output. Output should be the derivative. Then derivative should be equal to r times input. So the r times p. So r times p. So this is the simple function. So that I have created this file and save it in the my functions folder. Okay. Then what you can do is, if you want to run this in the different locations, since I am in my test scripts, so I need to add my functions folder to the Matlab path. So that is what I do here. So I can get the location, current location, present working directory, and the add path. You can add the my functions folder to the current location. So then I can add that into the path. Therefore, I can simply click here, then it will go look at my functions as well, folder as well. Then it will take whatever the necessary files. Okay. So that's just to get the simple PG. Okay. So it's there in my functions. If I click here, you can see that the simple PG. So that is there. Okay, I have already created, but I'm not. That's simply this one. Okay. Okay. So then you can simply use the ODE 45. So this is the way to use it. So you have the ODE 45, and then you need to put @ sign, t and p. These are the variables that you will input to the function. So the function is given as, then the second argument will be the function name. Here we have created simple PG, T and P. And then you need to give the starting time, end time. So this is a simulation. You start from 0 to 20. Okay. And then you need to give the initial value of the y variable. So we have one variable, initial population, in this case, it's 2.5. So this is the method. So this should be given into the ODE45. Then it will integrate, and then it will give the result at the time and the p. So it should be the p value is the y-axis and the p is the x-axis. So this is the way. Okay, so this is the standard way to call the ODE45 function. All the other functions will also call in this format. You have to give the inputs as a collection in front as at sign, and then you need to give the corresponding function. So this is just the format. Okay, syntax. Then it will integrate and it will give you the solution. So let me run this part. Yeah, simple as that. So integrate. You start with the 2.5 population, and then the time. In this case, time we can assume that it's in years. So it's 0 to 20. Start from 0 time, 20 years later, and the population will be follow the simple ordinary differential equation that we described. And then if you integrate, the population will grow something like that. Okay, and these are the plotting functions that we discussed previous time. Okay, so this is a very simple equation, ordinary differential equation. So let's talk about how to solve the system of nonlinear ODEs. So this way, we can easily solve nonlinear ODE as well. Okay, so only thing is you need to put that information into your encoding function or derivative function. For example, so let's consider the system of two first-order nonlinear ODEs that describe the population of predators and prey in biological lot. The prey population growth will be, of course, proportional to the number of prey, okay, available prey population size. Of course, it should be minus. The predators will model parameter. Okay, so so this is a system of equations that describe the predator-prey model. So you have a first-order system, nonlinear system, because you have multiplications of x and y's, the two variables in a single term. So that's why it's nonlinear. What you can do is you can simply convert this into the derivative function. So the dp dt should simply compute this derivative to the right-hand side. So what you do is the time and the p. So the p is a vector. P is basically p1 will be x and p2 will be y. Okay. So assume that alpha beta is constant 1 and delta b. So alpha gamma is constant 1 and the delta beta is 0.02 and 0.1. So you can see the interactions depending on the interactions, whether which one is. So that's totally from the experiment. Okay. So for the time being, let's assume these are the values. Then what we need is to compute the derivative dp dt. So you know alpha. So we can take the x out. So just to make it simplify. So if you take x out, it should be alpha minus beta y multiplied by x. So the x is the first variable of the vector. So we give p1 as the x. So the p1 multiplied by alpha minus beta y. So y is the p2. Okay, and then the second. multiplication is the element-wise multiplication. Okay, that doesn't matter. So it's simply multiplication. Okay, so this will compute the right-hand side, and it will give out because this is the derivative. So this is corresponding to the dx over dt. So the dp dt one will be this will also be 2 by 1. So this is 2 by 1 vector, and the first one will be the first half, and the second one will be the corresponding to the y value. Okay, I think that is clear. So this is also I have created. So this is just a code snippet that you have to create, and then you have to store that in the whatever the location. So here I have put that into my functions folder. So you have here you can see that lotka od. So the name should be lotka od, the same. Okay, so then you can call our ordinary differential equation. Of course, this is to simulate initial values. We start from time equal to 0, and the final time 15. So our time simulation will be 0 to 15, and the population, initial population, we need to do now. It's a vector because we have x and y, and 50-50. So we have the same population of prey and predator. So this is x and this is y. Prey is 50, predator is 50. So the same population for both initial. And then we can call the OD45 at lotka OD, and then you can give the T0, T final, and T0. Okay. So you can simply call the OD function. So you can see that. So in this situation, you can even directly call without putting the variable in front of it. In the previous example, we give you at TP and then this. Okay. If you are not using at TP, you can simply call the at function without putting this TP. Okay, that's another way to call it. Okay, so then it is intuitive for the Matlab. Okay. So now I can integrate that system of ordinary differential equations, two differential equations, and non-linear ordinary differential equations. Only thing is with non-linearities, we need to compute that in the derivative function. So then you can see that you start with the initial time point 50, predator and the prey. The predators are represented in red curve and the prey is the blue curve. So you can see the predators initially the growth is less, and then after some time when the preys are going up, the predator population grows up, and when it is going up, of course the prey population will go down because a lot of predators are there. And then when the prey population is going down, then there's no more food for predators, so their population is going down. Therefore, so there's a cyclic variations. Okay, so this is the common problem model of the population, predator-prey population model. And of course, if you have this periodic the variations, then what you can do is usually you can use phase plane to look at. That's basically you plot the two variables, x and y, the prey and the predators, so as x and y. So then if there's a cyclic variations, you will end up with this cycle in the phase plane. So you have the prey population and the predator population, the xy graph. So you can see that the prey population is varying from 25 to 85 and cyclically, and then the predator population is varying from 55 to 160, something like that. Yeah. So that will show you the cyclic behavior. And so, of course, so that's a very simple solution for the nonlinear problem for the system of differential equations, and we can use this for multiple initial conditions. So if you want to give a multiple initial conditions, so luckily we studied for loop, you can include a for loop. For example, if you want to change the y population, that's the predator population, from starting from 5 to 100 with steps of 10. So you will have in one loop, you will have one value of different value for initial population of the predators. So then you can check what happens to the rest. What the initial population of the prey will be the same. So this is our call OD45. You can see that T0 T final will be the same. And the initial population x is 50. It's constant, but the predator population, that's y, will be different in the different loops. And then we can run it and you can see what happens to the. If you can plot the phase plot to see the variation. Okay, so depending on the initial populations of the predator, so you will have different variations. So it's just to see. Okay, so there are a lot of information you can read from. Okay, so let's solve the system of ordinary differential equation in vector form. So this will be useful if you convert that into vector form. It's kind of similar, but then if you have a larger system of differential equations, then you can make it the solving or the computational time requirement can be reduced if you convert that into the vector form. Okay, so that's useful for faster computation, and especially for if you have multiple initial condition. If you want to check, then you can use this, convert this into vector form, and the multiplication can be accelerated. Okay, so this here also I'm using another biological module, that is famous Belousov-Sobotynsky reaction module. So it's an example of a chemical reaction that results in cyclic variations in concentration of the region. So there's one proposed method module for such a reaction system, the cubic autocaloric. So this is the system of equation. d by dx over dt, x and y are the concentrations of two reacting chemicals, and this is the relationship between these two. So we can convert that into vector form. So that's dx over dy, and this is the same point xy, but of course you can see that it's non-linear. Sometimes it will be easy. If it is linear, you can convert this multiplication even further, vectorize. Okay, but in this case you cannot vectorize, but the only thing is you can have 2 by 1 vector. So then dw over dt, so the w is xy, will be function of dw. So it's kind of similar in the previous example as well, but now it's in the vector form, the same vector. Okay, so now we can we create the derivative, CCL. So this is the catalytic this is the name for the derivative function, and you input t and w vector, and of course you can inside to make it clear for you, you can make variables x and y here, but that will reduce the efficiency. But most of the cases you can use w vector 1 and w vector 2 directly instead of x and y. You can replace this x with w vector 1 likewise. Okay, so then you can even reduce the memory requirement as well. But anyway, so this is just for the intuitiveness. Okay, so if you put x and y, so you can simply write down the same equation here, and x and y will be taken from the y vector, and then you send the dx over dt and dt as the column vector. Okay. Then the time range. So this is the time range is for the simulation time, and the initial values, and initial w vector then should be it should be a vector. You can concatenate with the initial values of x and y, and the numerical integration can be done in this way. Okay, so it's kind of similar. So if I run this, so instead of ODE 45, you can test with the other available ODE solvers as well, just to check whether you will get the results. So you can see the time evolution of x and y chemicals. Okay. Again, here you can use the phase plot just to see whether how the reaction going to be settled. So it initially start with some unstable point, but then ultimately will end up with a cyclic behavior, something like that. Okay. And certain situations we can put so there use some options input to the ODE differential equation to kind of to make something that make out of something that we want. Okay, so for example, we can modify the tolerance limit and using the ODE set command. So the ODE set. So as an input, we can send the ODE 45. The options can be set using ODE set. The ODE set can be of different. There are a lot of inputs that we can change. So if you simply look for ODE set, help ODE set, you will get all this. Okay. So one important thing is we can use the event detection for this purpose. Okay. Sometimes we are interested not in the time evolution, but we are interested in something happen. For example, since these two are started at two different levels, two different concentrations, if you want to find out when these two concentrations are equal, at what time point. So if you want to find out that point, what we can do. So we can use this ODE set command to define an event, and then we can use that event function to solve such a problem. Okay. So for example, if you want to handle the events when integrating, if you are interested in learning about something special, as I mentioned, then you can use this event function. So the event function you can define. So these are the event functions. This is a standard event function. So you have the event, and then you have the stop, and you have direction. So direction is, you can define, in this case, if it is 1, we detect only when the events are increasing. So the derivative is in the positive direction. Okay. If it is negative, if it is, then it will, if it is going equal, event will be 0. That means there will be event detection. So we can set that as an option. So the options ODE set. So we can set the other parameter, relative tolerance, and then the events. So this is the call for the event function, and then we can call this function at TW event function TW. Okay. So this is the calling function for this one, and then we can use the same normal integration, but with the options as an additional input to the ODE 45 equation. Okay, if you put 3 dots in front of it, you can write down without write down in the same line, you can write down the next one in the next line. But for that, you need to use these 3 dots. That's in the method. So that we discussed in the first session. Okay. So this is the same integration. Only difference is we have options, and in the options we have set an event function. So if I integrate, of course, now in that case it will stop when these two are equal. For example, in this case. So this is the initial integration. So it starts, and then we set that initially, of course, these two are equal, but we need to find out when the concentration increases. When the concentration increases of 1 derivative. So this is 1, detect only events dEdt. So that, I think it's a second variable. Yeah. So when it increases, so at this point it increases, and it will stop. So these two are equal at this point, and then there will be no further integration. For example, this is the same equation. For example, this is only this part. Yeah. So at this point, it is going to be equal. Okay. And this actually, it should be in this case. This not the first one, the second one. It will stop after detecting the equality between x and y. There will be no further integration. So that's why that. So that event detection can happen. Okay. So this is just to show the difference. So if you plug the solution x minus x minus y minus x, so you can see that. So this it will be 0 at this point. So there's no difference. That means equal. Okay, so that's one way to use the event function. And the other important one is in some cases you do not need these ODE solvers for simple computations. You can use such as forward Euler methods or Runge-Kutta methods. Maybe you have heard these Runge-Kutta methods. There are different orders. Depending on your accuracy, you can use first order or second order, fourth order, likewise. So I have included a file, fourth order Runge-Kutta method that I developed for some other purpose as well. And of course, you can use the forward Euler method if the accuracy is important, not that important. But of course, in most of the cases, you can use this Euler method. But only thing is, you can reduce the time step. If you reduce the time step, the accuracy will be higher. Okay. So if you are not going to use the ODs solvers provided by Matlab, if you're interested in the your own one, then you can use this forward Euler integration. So it's basically the derivative. Derivative is given by dy over dx fxy evaluated at x0 and 0. And derivative is the tangent of the, for example, in this point, it's a tangent of the curve. Okay, so that can be written in this way. You know, another point, and then if you want to find out y1, that is, if you know the initial condition, y0 plus h times the derivative evaluated at this point. All you need is this information. So this is the forward Euler method. So you know the initial condition and you know the time step, and then you can evaluate the derivative because it is given, because this is known, this is the system, and we can evaluate that at that point, and then you multiply by the time step and then add to the initial condition. Then you can integrate again and iterate. Iteratively, you can do this again and again in each time step. So therefore, that can be done very easily. So for as an example, here I have used the Hodgkin Hubsan model for the membrane voltage of a nerve axon. So this is a complicated. You have 3 channels, 2 channels of the potassium and sodium, and then you have the gate opening mechanism. Of course, I'm not going to explain here the model, but only thing is that can be described using system of first order differential equation. So these are the differential equations. You have 4 differential equations. At the same time, you have algebraic equations as well. And you can combine these into a derivative function, and you can compute this if you know the input as the membrane voltage and all these variables, and then you can integrate that using the first order Euler equation. That I have done here. Okay, I'm not going to explain the. So these are initial conditions, and then some of the parameters, and only the thing important for us here is this integration. So you start with the initial condition, and then you do. In this case, we have the time step, and then I have given you give a current impulse, the current pulse at a certain point, and we have the current vector, and then we know the time derivative, time point, total number of time points that can be computed by this one, and we iterate until the end of this time interval. Okay, so then you start with the initial value, then this is the integration that I wrote about. Okay, and this is for the voltage, and this is for the other derivative functions. You have the initial input and the time distance, and then the whatever the derivative. The derivative should be computed by these equations. These equations are given. So this is the derivative, and the voltage derivation is given by this. So that can be simply computed here. Okay, so that is that. And only thing is, we know the derivative computed at the current point, and then multiplied by the h or the time step, and then you add the initial, and then you will get the next step, next time step, value at the next time. Then you do it iteratively to obtain the integration of the whole result. Then you can plot this. So if I run this, so don't worry, you do not need to understand it here, but carefully look at this when you have the files. Then you will see that it's very easy, even though the model is complicated, but you can use the simple integration without using OD solver, simple Euler equation to solve it. So it's now running, since we have a large number of derivative equations, it will take time. Okay? And then you have the plotting, and then you can see that. So you have the initial membrane potential, and then you have the current impulse to the neuron. You will get the spikes. So these spikes are represented by the Hodgkin formulation. So depending on the concentrations, and then the voltage, so you will get this spike. So this is an example of solving the system of equation by using simple Euler method. Okay, without using the. So if you want to use the more accurate versions, you can use this called method of fourth order solver. So here I have prepared one. This is also included. So this is the file. So you can use this. This will be similar to the OD45. Okay. So, but it's simple than that. Okay, and then there are ways to solve the analytical solution, to get the analytical solution as well. For that, you need to have the Matlab symbolic toolbox. Okay, if you have the symbolic toolbox, then you can solve the analytically the system of differential equation using the solve command. So, but I should mention that most important part is the numerical solution, because most of the cases you are not interested in analytical. So sometimes it is impossible to solve analytically the system, and then it's always you can solve it using numerical techniques that I mentioned. But part can be very easily computed using A into Y. So A into Y, so you can see that you can get the differential equation. The system of ODEs can be represented in this format. Then you can give the initial condition. You can find the initial condition. Y0 is given 0.1, and you can use the dissolve command using the system of ordinary differential equation as the input and the initial condition as the input. So this will solve analytically and give you the result out. Okay. So if I click it here, so this is the system of differential equation ODEs, and the solution is this C solution, T H solution, C and H. So you can see that it's been analytically solved. Okay. And of course, you can visualize. You can use the fplot function to visualize this H solution and C solution. So you have initial conditions, and then you integrate the function. So this is the solution. Okay, so that's a very brief introduction to solve the analytically using systems. And as I mentioned, the differential equation as well as the difference equations is also important, as same as the differential equation. So if you use the difference equations, most of the time this comes using the discrete time situations in most areas, and it kind of get rid of calculus. Okay, so this so there are two types of problems. For the linear problems, this will end up as, for example, using Markov chain models that we described when we described the matrices, arrays and matrices in the first session. We can use the simple matrix multiplication to obtain the solution for the system of differential equations. But when it comes to the nonlinear problems, then we can use different techniques. So that I will discuss here. Okay. So for that, I will use an example that is the SI model of infectious diseases. Since these times we talk about a lot of COVID-19, so we can use this SIR model, susceptible, infected, and immune model for infectious diseases. So if we consider a population in which a contagious disease is spreading, and these are the groups. Okay, you have the susceptible group, those who may catch the disease that are not currently infected, and then there are groups of infected individuals who are currently infected, and then there are removed groups, That's individual who are no longer infectious. Maybe they are recovered, they have acquired immunity, or they have died. Of course, when you model this, you have some assumptions. The total population will not be different. So that kind of reasonable assumption. And if you have the transmission and infection rates and also the recovery rate, that can be computed using experimental data for a certain time. So the SIR model for such a system. So the infectious diseases can be given by this. The total population will be constant, but this can be described using the difference equation. Basically, you have the current time step, and you predict the next time step using the current values and the previous values. Okay, if it is first order, you will only predict the next output. Okay, so in this situation, the k is the current, and the k plus 1 will be the next. So if you this is the this is the model using SIR model for the using difference equation. So what we can do is we can convert this in, and very easily we can solve this system using iterative technique. So that's what I have done here. So you can iterate. First you need to compute the initial values. So in most of the cases, the initial values are given, or else you can obtain by simple computation, and then you can integrate from the next step to the whatever the time you want. You can simply implement the difference equation with the same given. So you know the previous values as the initial guess, and then you can compute the next one, and the next one will be the input for the next iteration. Likewise, you can simply iterate these through over the time, and then you can plot the result to see what happens. So that is kind of easy. Okay, in this case, I think we have some. Okay, anyway. There's some error. Okay, that's. Okay, yeah. Okay, so the system is there. Now we can initialize, and then you can see that. So the susceptible group is decreasing over the time, and the infectious group initially going up, and then it's going down, and then the recovered group increasing after some time. So at the end, you can see that there's no the total population is recovered. Okay, at the middle, you'll have a peak. So this is kind of SIR model for the influenza infectious. Okay. And of course, there's a modeling in second order nonlinear difference equations as well. That's again in the previous case, you can convert that into the first order difference equation. So I will stop here. I'm not going to talk about it. It's kind of similar that we did, but I will go to the, because time is limited, I will go to the curve fitting. Okay, that's really important for us. Okay, so this is very, so for in Matlab, there's a curve fitting toolbox known as CF tool. So you can use the CF tool app, or you can use available functions from the toolbox. So, or else, if you do not have the Matlab toolbox, curve fitting toolbox, so I have given you an example that you can use the linear regression or the least square method to solve without using any of these F4 commands. Okay, so the fit options in curve fitting app, you have different methods available: linear and nonlinear regression, interpolation, smoothing, and then you can have plotting and the other post processing available in this app. Okay, so that's possible to use if you have it, but if you do not have, you can use basic principles, the least square method, at least least square method to fit a polynomial to experimental data. So let's start with the programmatic curve. That is without using the app. You can use commands available to fit a line. Okay, so most of the cases here I will start with the polynomial curve. You can have different order of polynomials to fit. For that, we need data. So I have census data. That's basically population data. So this is the variation given in the time as years, and then the population growth in the other direction. Okay, if you want to model based using different, if you want to fit a curve to describe this variation, you can use the fit curve. Fit command, and the fit command with different polynomial types. You can have the polynomial of order 2, polynomial of order 3, or exponential. So if you search help fit, so it will give you the options available. So this you can directly call fit the data, y data, and the x data, and the y data, and the order of polynomial that you need. Then it will give you the goodness of fit, the available, and also the fitted curve. Okay, as a structure. So you can simply use this pop2 to plot the data. So it will give you the both time and the predicted values as well. Okay, this is just a simple way to use the plot a quadratic assumptions, the quadratic polynomial to fit the line. So you can see that it's quite very well fitted. If you want to increase, of course, these are the method. So you can do this again and again. Okay. So you can vary the polynomial of order 3, order 4, order 5, order 6. So this is just for you. I have 6. So you can normalize the data. So that's another way to do that. So that's just some modifications for the data, but it will not change the shape of the curve. It just normalizes the data. So you can use that same command, and exp1 is to use the exponential variation, and then you can plot everything together. Of course, you can see that when you increase the number of towards the end, fit. So all these parameters will be available here. So you can see that sum of squared error and the R square and the degree of freedom of the error and the adjusted R square and the root mean squared error. Okay, by looking at this, you can compare different models. Different models can directly call by using the output from the fit command. POP3, POP6 are direct output from the fit command. And if you simply click it, put it into the command window and enter, you can get all these results, and also the confidence intervals for these parameters. For example, POP3 is the polynomial of order 3, and these are the coefficients P1, P2, P3, and P4. Those coefficients values are given here, and the 95% confidence intervals is also given here. By looking at these, also you can get an idea whether this is good for this fit or not. Okay, so this is I quickly went through because it uses given commands in the Matlab toolbox. But most of the cases, if you do not have Matlab, of course you can use Octave. It's free available. For that purpose, it's better to use this direct application method of least square. Okay. So as I mentioned in the previous, the least square fit, you can assume a polynomial, linear least square fit. For example, if you assume the second order polynomial, and these are the variables, so this will be the order, and we can convert this into the system of differential equations. Sorry, it's a system of equations. in this format. Okay, so y1 will be our measured output, and the p1, p2, p3. So p1, p2, p. Okay, this order should be different. P's. Yeah, that's good. Yeah, p1, p2, p0. Then if you multiply p1 times x1 squared and p2 times x1 and p0 plus, that will give you the observations. Okay, so that is of the form y equals AB. So the A is the data matrix, X data matrix, and Y is the Y data. We know. So if you do the experiment, we know all the X1s, and also you know the Y1s. If you have the X and Y, X1s and Y1s, you can easily compute these two matrices. Okay, if you know A and Y, what we need to find out is the B. So the B can be obtained by, as I mentioned in the previous case. So if you have larger number of data points compared to the number of unknowns, here number of unknowns 3, but of course you can have large number, maybe hundreds of data points. Then it will be a least square problem. So the solution will be a least square problem. If you have the exact number of equations, if it is 3 equations, then you will get the exact solution. But since you have the large number of data points, so this will be a method of least square, the least square approximation for the system of equations. Okay, so you can directly compute this one, or else you can use this equation. Okay, so this equation to obtain the solution or the coefficient values. So let me introduce the example. So the same example, if we can go. So these are the data. So what you need to use if you are going to apply a second order polynomial, of course, then you need to compute this matrix that you should compute. You have the ones, and you have the X data, and then you have the X1 square data. If you are going to increase this to a third order, then of course you need to increase here the cube of X1. Okay, since we are now only dealing with the second quadratic form, so you will end up with X1 square. So you can create that using simply, if you know the Y data, sorry, X data. So this is the C data is the X data. You can have the element wise squaring by using the element operation. So this is the column of X squared, and this is the column of X, and this is 1. Okay, so this is the matrix A, and you can the population is the Y that we know, that's from the previous data, and we know Y and we know A matrix. We can simply compute what is B. Okay, so you can use either ML divide as in the previous case, or you can use the B backslash operator. You can use the inverse, the equation that I mentioned before. So all these will give you the same result. Okay, and also, so if I compare this with the POP2 model obtained from the fit function, so this is that. So this is so this should be the coefficients, 3 coefficients. You can see that they are exactly the same obtained from the fit function. So without fit function, you can use simple the backslash operator to obtain the least square method. Of course, the fit function is polynomial, and this polynomial, there also the toolbox is used the least square technique to obtain this polynomial coefficient. So these are the same. Okay, and the good thing, then if you want to compare the different models, then you need to compute the coefficient of determinants, that's usually known as the R square. So it's kind of a way to represent, it's a kind of way to explain how well the model can predict the data given the experimental data. Okay, so if you compute R square, then if it is, it will vary from 0 and 1, and if it comes closer to 1, that will be good. Okay, so this is the equation to compute, and then there are adjusted R square. If, of course, you know that increasing the polynomial decrease of freedom of the polynomial, you can fit a more curve. For example, in the previous example, you may have seen that if you increase the maybe linear plot will not be fit for the variation of the population, but the quadratic will fit, and then if you increase the maybe cubic one will fit more for the given data set. But then you increase the number of parameters. So that's the expense of the complexity. So to adjust that, you have this adjusted R square. So that basically you multiply the R square with the effective degrees of freedom by using this equation. The n is the number of data points, and the d is the degree of polynomial. So you reduce it and then you adjust it, so that you will get the adjusted R square. Okay. And all these goodness of fit parameters I have computed using our method for the method of least square without using the toolbox. So you can simply compute the sum of squared error. So you know the population. You know the real predicted values, and you know the observed values. The observed values are the y here that's given, and this pop2 LR is our predicted value. If you know the difference between these two, and you can square them up, that's the error. So you can get the sum of squared error. Okay, so that's the SSE. And for compute the R square, you can use the previous equation. And of course, here you have to use the mean of the y data in this case. Okay, to compute the sum of squared residual, that's the same here. The sum squared total is you need to get the mean. You need to subtract the mean, not the actual values. Okay, the predicted values or something. So it's the mean. It's the actual value minus mean of y. Then you can compute that. And for the adjusted R squared, you simply multiply it with this factor. And for the degree of freedom of the error is basically the total number of points minus the length of B vector, the length of population vector, the length of polynomial. So that's the number of degrees of freedom you subtract, so that you will get the degree of freedom in the error, effective degrees of freedom. And the RMSE is basically the square root of the sums of squared error divided by the DFE. Okay, so if I compute this value for our method of least square method, okay, but I think I have to run this one here. This one also to get the values. This is to get the predicted values. Otherwise, it will not be there in the to compute this. So then only I can compute. So you can see that the standard sum of squared error and the R square, adjusted R square, DFE, and RMSE computed using the first principles are matching with the things we obtain from the fit function. Okay. Okay, so that's a very simple curve fitting, and that of course, if you want to, that's for the linear curve fitting. If you want to use the nonlinear curve fitting, so then there's another function, n-lim fit, so the nonlinear fit. So you can use that here. Of course, I think since we are running out of time, I will stop here. That's because it's better to some questions as well, and or else you can use the curve fitting app. So that's very easy. So it's just the CF tool. If you put this into the command window and click it, so you will end up, you will get the graphical user interface for the curve fitting. That's an app. So you can use that. Very easy. Okay. So this is to select the data, and this is to select the method or the whatever what you want. So maybe a polynomial of degree. So you can change the degrees, and then you will come up results here. For example, if I say, for example, in our case, our X data will be C date, and our Y data will be pop. So, yeah. And it's polynomial of degree 2. So you can see that. So very quickly, so you can get the linear model of polynomial 2 with the P1, P2, P3 parameters here, and all the standard error, sum of squared error, R squared, adjusted R squared, and RMSE, all values are given here. And the equations and the plot is also given here. Okay, so that's very quick and very easy. But of course, for that, you need to have the toolbox. And if you do not have, but of course, you know, without the toolbox, you know a method to compute at least using least square method using polynomials. Okay. So, so that's all actually I have. Let me.